Welcome to this explainer. Today, we're going to unpack the mathematical secrets of algorithm efficiency, translating complex asymptotic logic and notation into intuitive, plain English. So if you've ever wanted to know how we actually mathematically prove how fast a piece of software is, you are absolutely in the right place.
Right. Let's dive straight into the fundamental problem here. Picture this. You've got two computers. One is this incredibly fast, state-of-the-art supercomputer, and the other is, well, a slow, decade-old laptop. If we run the exact same algorithm on both, the execution times are going to be vastly different. So how can we truly judge which algorithm is inherently better? How do we measure the pure logic of the code, completely independent of the machine it happens to be running on?
To solve that, here's our roadmap. We'll start with why we measure efficiency, then break down the big three notations, look at key asymptotic properties, learn how to prove the bounds, and finally explore strict bounds and beyond. All right, let's jump into Section 1, Why Measure Algorithm Efficiency.
What's really fascinating here is that to get a true measure, we absolutely have to abstract away all those machine-specific constants and implementation details. In the real world, sure, specific hardware or coding languages will heavily dictate how an algorithm behaves. But pure asymptotic analysis, it lets us focus entirely on the fundamental trends. It allows us to see that an algorithm running in n² time and one running in 2000 n² time are actually, mathematically speaking, asymptotically equivalent. We're studying the algorithm in and of itself.
And that brings us to what we truly care about, the order of growth. Visually, you can literally see how one function's curve eventually overtakes another as the input size, which we call n, stretches toward infinity. Think about it. An algorithm executing its primary operation 10 times n times is vastly better than one doing it 0.005 n² times. Why? Because as n gets massively large, it's that fundamental growth rate that dictates performance, not the constant fractions attached to it. Moving right along to Section 2, the big three notations. Let's zoom in on the actual tools we use to categorize this growth.
First up, the heavyweight champion, Big O notation. It's the most widely used tool in our kit. Big O essentially means our function is eventually always less than or equal to a bounding function. It provides the asymptotic upper bound. In plain English, it gives us a guaranteed ceiling for how long an algorithm will take. This is incredibly practical because it defines the absolute worst-case scenario. It tells us the maximum time required by the algorithm to finish the job.
On the flip side, we have omega notation. This one tells us our function is eventually always greater than or equal to the bounding function. So it provides the asymptotic lower bound. This represents the absolute shortest amount of time the execution will take, the best case complexity. Now, knowing an algorithm takes at least a certain amount of time isn't always as practical as knowing the worst case ceiling, but it's totally vital for a complete mathematical analysis.
And then we have theta notation. The crucial thing to remember about theta is that it acts as a tight bound. It literally encloses the function from both above and below. This means your function is safely sandwiched right between an upper and lower boundary for large input values. Because it provides these exact bounds, we often use theta to analyze the average case complexity of an algorithm, finding that realistic middle ground of execution time across all possible inputs.
Looking at these side by side really hammers home how execution time gives us different types of boundaries depending on what exactly we're evaluating. We use big O for the maximum time complexity, omega for the minimum, and theta when we want that exact average case bound. And notice how they all rely on finding positive constants and a specific threshold where the behavior consistently holds true as the input stretches to infinity.
Let's put this into a real-world scenario, maybe using something like the classic insertion sort. If you're looking to sort items, omega represents getting super lucky, like your data's almost entirely sorted already, so it takes lightning-fast, linear time. That's your best case. But big O, that represents having the absolute worst, completely backward data, where you have to check every single item against every other item, taking quadratic or n² time. If we want to use theta, we actually have to state both of those scenarios separately.
Okay, Section 3, Key Asymptotic Properties. Let's look at the math rules governing how these notations actually interact.
These notations aren't just random. They follow some very specific logical rules. Take the transitive property, for example. Think of it like this. If a function n is bounded by n² and n² is bounded by n³, well, then n is inherently bounded by n³. Makes sense, right? They also have reflexive properties because the maximum value of a function will simply be itself. These structural rules are what allow us to so easily manipulate and compare complex algorithms on paper.
Now, if you take one thing away from this section, make it this massive shortcut, the golden rule of asymptotics. When you're adding up complex polynomials, you can safely drop the low-order terms and just totally ignore leading constants. Why? Because the largest exponent is always, eventually, going to dominate the growth. For instance, if you've got an algorithm running at 3n cubed plus 6n squared plus 6,000, you can literally just drop everything else and call it theta of n cubed. The constant multipliers and the smaller terms simply stop mattering at all as n gets huge.
Which leads us to section 4, proving the bounds.
Now, intuition and dropping terms is great for a quick analysis, but definitional proofs actually show this physical dominance perfectly. Let's say you've got an algorithm taking 100n squared time and another taking n cubed. Even though 100n squared starts off way larger, looking at the math reveals that n cubed will always overtake it once the input crosses a specific threshold. In this case, exactly at an input of 100. From an input of 101 onward into infinity, the n-cubed function dominates entirely.
But what happens when you hit highly complex functions? You know, the ones with messy logarithms and fractions. Guessing constants becomes a total nightmare. So we upgrade to the limit method. We take the limit of the quotient of the two functions as n approaches infinity. If they diverge or converge on 0, calculus comes to the rescue, specifically L'Hopital's rule. By taking the derivative of the denominator and the numerator, we can find the exact, undeniable limits without any of the guesswork.
Finally, let's wrap things up with section 5, strict bounds and beyond. Sometimes big O and big omega are just a bit too loose because they include that or equal to condition. Enter little o and little omega. These provide strict bounds. Little o means a function is strictly less than another function, never touching, never equaling it. Similarly, little omega means a function is strictly greater than the bounding function. It's literally the mathematical difference between saying less than or equal to versus strictly less than.
And for real advanced analysis, we've got soft O notation, usually represented with a little tilde over the O. This is a super handy trick used to just completely ignore logarithmic factors. Why would we do that? Well, because logarithmic growth is incredibly slow. As our input approaches infinity, the impact of a log factor becomes basically invisible compared to polynomial growth. So soft O just sweeps it out of the equation entirely for a much cleaner view.
Ultimately, mastering all this asymptotic logic is really just about recognizing patterns. It means always keeping an eye out for simple algebraic shortcuts, like dropping constants and lower-order terms. It means knowing how to provide rigorous definitional proofs for the simple stuff, and, when the equations get rough, knowing you can default to the limit method and L'Hopital's rule to give you the tightest, simplest expressions mathematically possible.
So as you write or analyze your next piece of code, I want you to ask yourself a question. Are you just writing basic instructions, or are you actively mastering the fundamental mathematical limits of computation itself? Because once we truly optimize the asymptotic bounds of our software, the previously impossible problems of today, they become the everyday solutions of tomorrow. Thank you so much for joining me for this explanator on asymptotic logic. Keep optimizing.